So is there any questions or things that that are in the Slack channel that we should know about before we start?
I just want to mention, folks have sometimes found warnings with the Apple M1 chip when running the container. It's just a warning message. I get that on my Mac as well, and I haven't found any issues with that. But you know, you see that it's not a big problem.
Okay, well, good morning. We're going to get started here on our first session, which is the PyCSEP software tutorial. I'm going to start off with some background information on the CSEP project. CSEP stands for Collaboratory for the Study of Earthquake Predictability. And then we'll, after the kind of the introduction, I'll ask one of the research scientists who have developed the PyCSEP software to give us an introduction, and then we'll walk through the Jupyter Notebook tutorial. So I am going to, sorry, I'm just going to make sure I have my screen in the right format, just a moment. Okay, I think this should work. So, so welcome everyone. This morning, the first session is on PyCSEP software. I'm Phil Maechling. I'm software development staff at SCEC. The material I'm presenting has been developed by several collaborators, including Bill Savrin, Max Werner, and Jose Bayona, who will speak to us here in a moment. But to help understand the PyCSEP software, it helps to get a little bit of background on the larger activity called SCEC, which is related to rigorous earthquake forecast testing. So make a couple of points, a little bit about the motivations for SCEC, first decade, and then recent developments as we move from SCEC 1 to SCEC 2, and then Jose will give us the introduction to PyCSEP. So the idea of earthquake forecasting is, controversial field. It's quite common if we work at SCEC that, so SCEC is the Southern California Earthquake Center. People learn that we work here, the first thing they ask, oh, when is the next big one coming? And it would really be nice to be able to answer that. But it's very challenging, in some sense, unsolved scientific problem. That doesn't stop people from making statements that they can predict earthquakes. And there are controversial statements in public press statements that it's 99.9% correct, or their forecasts have this kind of success rate. So it's very difficult for public authorities to respond to forecasts, and particularly scientists or credible people who say they can accurately predict earthquakes. So CSEP was really formed to help develop a rigorous method to evaluate our earthquake forecasts working correctly. So instead of the field, they considers a prediction knowing in advance the time, location, and magnitude of an earthquake. That's quite difficult to do. But what is, in some sense, routine practice is probabilistic statements about strong shaking. And this is the field of probabilistic seismic hazard analysis. So the PSHA is, in some sense, the practice that scientists use, and prediction is not something that's considered available at this time. So there's a formation of a realm project to evaluate whether any of the kind of short-term earthquake forecast methods perform better than chance. This is a little bit background on those on that study. This is and it rigorously evaluated. I think there were 15 different methods for creating short-term earthquake forecasts. And some perform better than others. That was an independent kind of scientific study, but as a result, because it was providing useful information, a collaboration called SCEC formed, and to create a distributed laboratory and appropriate software tools, cyber infrastructure, to support a global activity, research activity on earthquake forecast evaluations. So SCEC was established at SCEC, but with collaboration internationally. There were basic principles that were introduced for the SCEC testing activity. Transparency, so that you could, the evaluation methods and the forecast methods were available to all the participants. The ability to compare earthquake forecasts, in some sense to state their results in equivalent manners, so that that the performance evaluations, they were comparing apples to apples, say. The ability to reproduce the forecasts, and the use of a controlled environment, so that people know which version of the software was run, what catalog version was used to generate the forecast. So these were basic principles that were built into the SCEC-1 system design. Another key aspect was, they're establishing rigorous testing. This meant that the forecasts were made for future events. So this were prospective forecasts. So basically, and then the system waited until the forecast period had passed, and then the forecast performances were evaluated. So this is based on the experience. It's much easier to predict earthquakes after they've occurred. So this idea of prospective forecast was really essential to SCEC. The evaluation system ran the forecast, and the evaluations ran for more than 10 years. And the system both ran the forecast and evaluated the forecast. It was an international effort. These boxes show organizations and testing regions that were developed: North America, Europe, New Zealand, Japan, Western Pacific. Number of models that were under test increased. There by 2016, there were over 400 different models. The time periods often varied. So some are 1 day forecasts, some are 1 month forecasts, some are 1 year forecasts. So, but multiple different forecasting methods were introduced. These were specific kind of uses for the forecast, kind of end users or the target communities. So the USGS was interested in operational earthquake forecasting. There were groups in Italy who were interested in evaluating their models. New Zealand had Christchurch sequence, and we're interested in evaluating forecast after that. There's Japanese effort to evaluate models for their country. So there was a summary of the CSEP1 results in this seismological research letter published in 2018. So for an overview of, in some sense, the results that came out of CSEP1, it's worth looking at this publication. Starting in 2018, a new development, in some sense a re-implementation, was started. And it had both scientific and technical goals. So scientifically, there was basically new types of earthquake forecasts that were being developed. Original CSEP1 was what we call grid-based forecasts. So in these, there's a well-defined region and a grid of cells, and the forecasts are asked to forecast or predict the rate of earthquake in each of the cells. So that's a grid-based forecast, and they have their own kind of evaluation methods. But during the CSEP1 operation period, new types of earthquake forecasts were being developed, called stochastic or catalog-based earthquake forecasts. USERF3 is an example of that. And a new kind of evaluation tests need to be developed for those forecast types. And so that was a scientific goal of CSEP2. There was also technical improvements that were needed. The experience running CSEP1 was it was difficult to extend. The software was complex and fairly heavyweight. And the testing computer infrastructure was time consuming to operate and expensive. So both of these goals, CSEP2 work was started to address both of these goals, the scientific and the technical. But the concept was we wanted to uphold the guiding principles from CSEP1 for rigorously evaluating earthquake forecasts. So a key element of the new CSEP, the CSEP2 development, is called PyCSEP. It's a Python software toolkit that implements earthquake forecast evaluation methods. There's a website, cseptesting.org, about the project, and there is a Git repo where the PyCSEP software is available. From the software's perspective, this gives kind of an overview of the components or what's built into the PyCSEP. There's tools for defining regions. So these would be testing regions. You have Cartesian grid or kind of multi-resolution meshes, polygons, tools for dealing with earthquake catalogs for retrieving and filtering out earthquakes, different kinds of formats for expressing earthquake forecasts, and then collection of evaluation methods. So those are the kind of the basic components that you'll find in the PyCSEP software. So that's kind of the introduction and overview of PyCSEP or the CSEP project. And at this point, I'd like to bring in our research scientist, Jose Bayona, who's a postdoctoral researcher, University of Bristol in Great Britain. He's been actively involved in CSEP research for several years. His research interests include statistical seismology and the development of earthquake forecasting methods. Here are a series of his recent publications. And I believe, Jose, you're going to give us an overview of the software grid-based forecast, and then we look at the Jupyter notebook.
I will do. Thanks, Phil, for the introduction. Let me share my screen. Can you guys see it?
Yep.
Nice. All right. Well, thanks everybody for attending this training session. As Phil mentioned, PyCSEP is a fairly recent effort that the CSEP community is doing or is currently working on to advance earthquake predictability research and also to support open science practices in academia. So it's very important for us to advertise let the community know that the software toolkit is out there, is publicly available, and this is a great opportunity to do so. So I hope this is useful and informative. There you go. All right. I'm going to start mentioning that, again, as Phil described earlier, currently PyCSEP users can develop, visualize, represent, and prospectively evaluate two different types of seismicity forecast against real data, against real earthquakes. The first family of them is our catalog-based seismicity forecast, which are defined by a list of typically thousands of simulated earthquakes. And the second family are grid-based seismicity forecasts, which are expressed as mean rates of seismicity within discrete space-time magnitude bins. On this slide, I'm showing two different plots that the PyCSEP toolkit can create. And in the interest of time, I'm going to only focus now on the evaluation of grid-based seismicity forecast. But I encourage all of you, if you're interested in learning a bit more about catalog-based seismicity models, on the evaluation of catalog-based seismicity models, to take a look at this paper that was published a few years ago by Bill Sabran in BSSA. And of course, you can reach out to us if you're interested. All right, let's dive in. So let's first suppose that we have a very simple testing region defined by two spatial cells, one red, one green. Easy. So each spatial cell is providing the number of expected earthquakes expected by a model at a magnitude threshold, at a predefined magnitude threshold in a predefined time span. So we have defined this testing region, and we can also model like what's the distribution of these seismicity rates according of as a function of magnitude. So for instance, a modeler can assume a Gutenberg-Richter type magnitude frequency distribution, and in the same cells, the model can provide what's the number of observed earthquakes, say at a magnitude threshold of 5, at a magnitude threshold of 5.1, 5.2, etc. Typically, at CSEP experiments, we use a very high spatial resolution, time one in longitude and in magnitude, and also the binning is quite is a very high resolution magnitude binning. It's a binning of 0.1 units. So this is a basic way to define a seismicity forecast. So once we have this seismicity forecast, we can take a look at the catalog and analyze if the observations are actually consistent with what the model is expecting. So at CSEP, we typically assume that the earthquake rate provided by the model is the correct earthquake rate, and we compute like what's the probability of observe the real data under the model, under this assumption. So it's another way to formulate like how consistent the model, the predictions and the observations are. So in particular, we evaluate how like consistency between the observed and the predicted number a spatial magnitude and likelihood distribution of earthquakes. In the interest of time, also, I'm going to focus only on the number and the spatial test. But yeah, I also encourage you to reach out if you're interested in learning a bit more about other tests that the PyCSEP toolkit is also providing. We not only provide, let's say, a consistency test, but we also compare seismicity models. So in other words, we don't only compare what's the consistency between the observations with the models, but we also compare the predictive skills of two competing models. So that is has been done by means of the comparative t-test, which is basically based on information gains, which is a metric that is telling us how much information a model is providing about earthquakes with respect to another benchmark model, which in this case I'm referring to as lambda asterisk. So let's dive in. Into the number test, SCEC test. So one of the assumptions that we are doing at SCEC is, we assume that earthquake rates or earthquake numbers in individual cells are Poisson distributed and are independent from the rates or from the numbers of earthquakes in other spatial cells. So of course we know that this assumption is quite could be quite controversial, especially in the cases when we have clustered seismicity, but this is a very first approach that we have developed because it's the formulation is quite elegant, and also the Poisson assumption has been used for seismic hazard studies, which is the ultimate goal of PyCSEP studies, like inform which seismicity models are the most informative so that we can reduce epistemic uncertainties in seismic hazard studies. So assuming a Poisson distribution, we can compute what's the probability of observing a number omega of real earthquakes given the expected value lambda that the model is providing. So in this very simple example, I'm showing you a Poisson distribution, which is centered in a mean value of about 28 earthquakes, and that's the distribution that it has. On the right-hand side of this slide, I'm showing you the number of earthquakes with a magnitude threshold of 5. That is, earthquakes at a magnitude threshold 5 or above, observed in California in the past 80 years. And we observed that, the Poisson assumption or the Poisson likelihood distribution is poor when it comes to capture the spatial temporal variability of seismicity. I'm not going to talk much about other tests that have been already, other likelihood distributions that have been implemented in PyCSEP by now. But I can tell you, for example, that when evaluating the consistency between the expected and the predicted, the predicted and the observed number of earthquakes, we are also currently using a negative binomial distribution, which captures better this spatial temporal distribution of seismicity. So basically, the end test is a test which is intended to describe how well the number of earthquakes, like how consistent the number of observed earthquakes is with respect to the predicted number of earthquakes that each model is providing. Let's have a look at the spatial component of the model. In this case, I'm presenting a seismicity forecast provided by a model that I'm going to be referring as HKJ, which is basically a model that smooths small earthquake locations. and provides this type of seismicity forecast. So let's have a look at this first cell in which we actually don't observe any earthquake. So we can compute what's the probability of observing 0 earthquakes given the expected value lambda that this model is providing. And that's given a Poisson assumption, a Poisson distribution. And that's what I'm going to be referring to as a log score, as a probability score. So I can take the natural logarithm of that number, and this is what I'm showing here. It's very important to note that the closer to 0 the log score is, the more consistent the observation with the forecast is. So we can compute these log scores in all the cells that are defined, in this case, in the California testing region. And for example, we can observe that in that cell where we observe 4 earthquakes, the probability of observing 4 earthquakes given the expected value lambda of 0.015 is actually very low. So that's what I mean when the Poisson assumption is very limited in its capacity to capture the spatial variability of earthquakes, especially when we have seismicity clusters. So we can sum, like in all the spatial cells, we can sum all these scores, and that's what I'm going to be referring to as the joint probability score, which in this case, for example, I'm going to represent here as a square. So that's the observed joint likelihood score. But we need to account for forecast uncertainties. So what PyCSEP is actually doing is simulating different catalogs that are consistent with the observations to determine whether the model is consistent with the spatial distribution of seismicity. So the first thing we do actually is to isolate, in the case of the S test, of the spatial test, we isolate the spatial component of the forecast by summing all by summing over magnitudes, so that we only have like the number of expected earthquakes at a magnitude threshold X in each cell. Well, in all the cells. Then we normalize this rates in each cell by the number of observed earthquakes, so that by doing that we are absolutely dealing with the spatial component of the forecast. Then we construct a discrete distribution by normalizing and summarizing the rates in each forecast. That is, we're constructing a function that in the first element we have the number of earthquakes expected by the first cell, and the last cell is going to have the total number of earthquakes in the whole testing region. So, for example, another fairly straightforward example. So in this case, I have a forecast that has 4 spatial cells, and in each cell I have 1, 4, 3, and 2 earthquakes. So I normalize the total number of earthquakes, and I assign, like cumulatively in each cell, I assign in each cell the cumulative number rate. So then, once I have this distribution, for each simulated event, let's say that in 10 years, I'm observing 40 earthquakes. For the first earthquake, I randomly select a number between 0 and 1. And let's say that random number is 0.23. So that 0.23 is going to be assigned in the cell that is closer, like that contains that number. So in that case, it's going to be assigned to the second bin of this distribution. So I can do it for the second earthquake, for the third earthquake, for the 40th earthquake, and then I can again compute what's the probability of observing such 40 earthquakes, simulated earthquakes, according to the model, and I'm going to obtain another joint likelihood score that probably is going to fall here. I can run the process 1,000 times, and I'm going to get a family of joint likelihood scores that are going to fall all over this place. And I can take the 95 confidence range of that distribution and observe and check if the observed joint likelihood score falls within this distribution. So in this case, for example, we were analyzing a model that we refer to as Lombardi, and we see that the observed number of the observed spatial joint likelihood score falls within the 95 confidence range, which is represented by these bars, which is telling me that in terms of in terms of the spatial distribution of epicenters, that distribution is consistent with what the model is expecting. In other cases, for example, here in the model for Melletti and Werner M1, the expected distribution of epicenters is not consistent with what the model is, with what the catalog is actually showing. So let's have a look at the code, where we actually have a couple of examples of how this is done. So maybe Phil, if you want, or sure, Fabio, if you want to share your screen.
Yes, yeah, I can do that.
But probably, like, are there any questions? Probably this was a bit too technical. Sorry about that, but you guys have any questions at this point?
Yes, so Fabio or Scott are monitoring the Slack channel. Is there anything in the Slack channel that we should address before we go into the Jupyter Notebook?
No questions at this time.
Okay. So
yeah, just to summarize, this test evaluate the consistency between the observations and the predictions provided by each model. In a nutshell.
Okay, good. So for those of you running the tutorials on your laptop, the stage that we're at is we have Docker installed on our computer. The Docker desktop is running, and I have opened a terminal window on my computer on my Macintosh and run this this command here. So this is, if you type docker run these ports and indicate this image, it will retrieve it. It retrieved it from Docker Hub. I also did these steps. So my terminal window, I did the run command, and then it opened up and it printed this material, and there's a URL, and I've posted that into a browser. So, and once those steps were completed, this window, a Jupyter Notebook window, has appeared in my browser. What you'll see there are two Jupyter Notebooks we're distributing in this tutorial image. The one we're going to look at is the PyCSEP tutorial gridded. So we want to select that one. And then this brings up the notebook itself. The key for this is, for going through these notebooks, since this is the first one we've gone through, is the cells. There's cells. This is a cell, this is a cell, and there's really two main types. One, this is a text or markdown cell, so that's largely informational or material, reading material. And then this is a cell that has Python code. And the PyCSEP software is installed in here, and so we can basically interact with the Python software in a code cell. So the other, I think, one other basic is how to proceed from cell to cell. There's a run or a step arrow here up at the top, or you can type shift and enter key and it'll progress one cell to the next. Okay, Tony, that was kind of the intro I want to make sure we talked about. And so we're here at the top cell that's selected. Let me know and I'll move us to the next cell.
Thanks, Phil. Could you please enlarge the page?
Sure. So
Thanks a lot.
let's see.
All right. So basically, this tutorial is going to show us how to evaluate and compare two time-independent seismicity models for Italy. One of them is a model created by Verna in 2010, and the other one is a model created by Lombardi. No, by the working group of Italy that created the national seismic hazard model. So that's something that is actually quite interesting. So we can dive in. So the first part of the Jupyter notebook is basically importing all the libraries that we're going to use to conduct this study. So if you can run it, Phil, I would appreciate it. Right. So one of the premises of PyCSEP is to be able to fully prospectively evaluate seismicity models, and that is like evaluate the consistency of these models against future out-of-sample data. So these models were calibrated with data before 2010, so that the evaluation uses earthquakes that are not used to calibrate these models. So in that sense, the evaluation is completely prospective. So we're going to run an evaluation using 5 years of prospective data, starting on the 1st of January 2010 and ending on the 1st of January 2015, which is what the next bit of code is doing. Then we're gonna load both forecasts. Actually, those two models are implemented in PyCSEP as an example. We have examples for Italy, for California, and we're going to use these two for the purpose of this workshop. So could you, yeah. There you go. Yeah, this is just a sanity check. All right. This other function is basically defining like things that we're gonna use to make our plots look a bit prettier. So we can run them. This other functionality is a very straightforward way to represent the seismicity forecast created by Verna. And this is the way it looks.
Yeah, I'll comment there. If there's a star here, it means it's processing. You can also look at this kernel, whether it's busy, to see whether the notebook behind the scenes is calculating things.
So that's the way the seismicity forecast looks like. In this case, we are showing the number of earthquakes at a magnitude threshold of 4.95 that the model is expecting in each individual cell. Remember that the spatial resolution was quite high. So like if we zoom in, we can see that this map is formed with spatial grids. And in red, we see regions where according to the model, we are expecting higher seismicity compared with the regions that are represented with blue, purple-ish colors. So that's basically what this function is doing. Next, please. Probably if you Phil can copy paste the same code, but now using the Meleti forecast, the
Sure.
participants could see
Yes.
the way it looks.
So this is a first kind of exercise for the participants.
Oh,
So,
okay.
But yeah, the idea is with the notebook set up 2 different forecasts earlier, the Werner forecast and the Meleti. So this, we plotted the Werner and question, how can we plot the Meleti? And as I understand, it would be quite similar to this, but we would use this other forecast object here, the Meleti forecast. So
Exactly.
I'm just going to use the same kind of formatting, but change this. 2 T's, Meleti? Or
Meleti,
okay.
M-E. And please close the parentheses after parts detect.
Okay, I'm just going to check back. So we're trying to reference this forecast. So Meleti, spelled that right. And I'm hitting Shift and Enter. Let's see if we processing. Yep.
Just for the participants to know, the Werner model is so every seismicity model is based on the assumption that the modeler thinks it's appropriate. So in the case of Werner, they assumed that the use of small earthquakes, like small earthquakes, are informative in forecasting larger earthquakes, and they adaptatively smooth the location of small earthquakes, very similar to the HKJ model in California. They apply the same method in Italy, which is a scientific hypothesis. Like, I use small earthquakes to forecast large earthquakes, and we compare how good this, we evaluate how good this hypothesis is against real earthquakes. So in the case of Meleti, this is a model that is based on a tectonic or a seismic zonation in Italy, that each of which has its own seismicity parameters, its own seismicity behavior, let's say. Again, red regions indicate that the model is expecting high seismicity, and blue, purple colors denote the opposite. So you guys can see that there are differences between the 2 models.
Yeah, and I add in just a couple on your comments. So one, to me, this is a indication, an example of kind of the international aspect of SCEC and PyCSEP, that the tools have been developed collaboratively, and they're being applied to multiple international regions. The other is kind of interesting of this forecast seismicity for Italy. There was a well-known earthquake in L'Aquila, and does it fall into these red zones? Are these
Yes.
Forecasts? So that would have been part of the forecast potentially. So, okay.
All right. So we have defined the testing region. We have 2 competing seismicity models. We need the real data. We need to see how consistent these models are with those data, and we are going to compare them later. So for the Italian experiment, for the Italian case, let's say, the developers back in 2010 decided that the Horus, I don't know how to pronounce it, but the seismic catalog produced by the NGNV, it was going to be the authoritative earthquake catalog. And that's exactly what we're going to load right now. All right. So the second step is, so like once we have uploaded the earthquake catalog, so the seismicity is going to be confined within this rectangle, which is slightly bigger than the Italy testing region. So the next function, what it's doing, the next function is to filter earthquakes and include all of the earthquakes that are within that SCEC Italy testing region only. Then the next filter is we're interested in assessing the consistency of earthquakes at a magnitude threshold of 4.95 with the forecast. So we get rid of the small earthquakes, the earthquakes that are not at this magnitude threshold or above. So that is what this new function is doing. So yeah, we can probably.
Yep. So now this is another exercise for the participants. So we've filtered the catalog to the grid-based region for Italy, filtered out the extra or the earthquakes in the catalog, anything lower than 4.5. And I think the exercise is how many events are left in the catalog. I think maybe it's because we can just print this object, which is a test catalog object, and then it'll tell us we've got 13 events in the catalog remaining, which is what we expected.
You can also plot the catalog with PyCSEP fairly easily. If you type, sorry, Scott. If you type Italy test catalog dot plot parentheses.
I'm sorry, Tono, if you start over and I'll type it.
Italy test catalog dot plot. Exactly. Scott, you had a question.
Yeah, someone in the Slack channel had a question.
Yes.
Tim, would you be willing to unmute and ask?
Yeah, sure. So I was just wondering if there's any way to do with the model, because so far we've been playing around with the validation part, but I was wondering what to do if the model does not match the observation.
Can you elaborate a bit more about that question?
Yeah, so so far we've been playing around the this kind of validation step. So just trying to compare our model with the validation in the future.
Yes.
But my question is, what if the model does not match the observation? Is there any way to adjust the model?
Yes, I mean, you could do, like, you can retrain your model to match the observations, but the evaluation in that case wouldn't be absolutely, like, truly prospective. Like,
Tonya,
it's also, yeah.
Maybe I can help. So I think maybe question relates to, can we modify the model within PyCSEP? And I don't believe the forecast models are currently part of PyCSEP. Is that true?
You can create another model.
Yes. But yes,
You can do that.
Okay. I think, was that the spirit of the question is, can you, for example, create a new version of the Werner model or modify that and retest it? Is that what you were asking?
Yeah. I mean, yeah,
Let me state, so CSEP 1, the model codes were included as part of the overall suite of collection of CSEP software. In PyCSEP, the models are sometimes broken out, and there's an expectation that they're basically contributed as source code to some permanent repository, and then put under evaluation by PyCSEP. So the model codes themselves are treated or handled independently in the new CSEP 2. So, yeah. Is that fair, Tonya?
Yes.
Okay.
Does that answer your question, Tim?
Yes, thanks.
No worries.
So this is the outcome of plotting the catalog. So just I think that's a good example of the kind of the power of the PyCSEP is we've got the catalog and then very easily kind of plot the events that are in the catalog with just one line of code.
And of course, like you guys can define the arguments that you would prefer. Like instead of circles, you can use squares, or like instead of using that color bar, you can use another one. That's something that you can adapt to your own desires, let's say. All right. Okay. Then yeah, let's run the spatial test, which is a very straightforward way. I mean, the way to do it is very straightforward. So for this function, you guys only need 2 arguments, one the forecast and the other one the catalog.
I'm sorry. So we've run the consistency test here. This ran the one for the Werner results, and then there's an exercise here to run the one for Maletti. And I think it's
so this line of code is basically computing, again, the joint likelihood score. The spatial joint likelihood score is running all the simulations for the simulated joint likelihood score distribution, and it's assessing whether the observed spatial joint likelihood score falls in the confidence range of simulated joint likelihood scores. You're missing an E in forecast. There you go. So you can write the results. Also, in the interest of time, because we have only 5 minutes, you can put some arguments for plotting the consistency test results. And if you run the next function, we're gonna.
I'll just point out this cell that output to a JSON file that has showed up in the notebook directory up here. This is the JSON file that was produced. Okay.
and you can plot the results. So basically, this results is telling us that the spatial distribution of earthquakes expected by the Werner model is not consistent with the spatial distribution of observed epicenters is not consistent with the spatial distribution of expected earthquakes given by the Werner model, whereas the Meleti model is more consistent in space than the Werner model to forecast where these earthquakes are going to occur, where these earthquakes in this independent five-year evaluation period are going to occur. So that is what this model is telling us. And again, the closer to zero the observed joint likelihood score is, the more consistent the model with observations is. All right. So we can compare these two models using the paired t-test, which again depends on information gains. This is typical, like when we have only two models to compare against, that happens. But if we have more than two, that index zero disappears. But basically, this plot is telling us, like, the reference model in this case is the Meleti model. So we are computing like how much information the Werner model is providing or losing with respect to this model, and falls beneath the line, the dashed line, which indicates that the model is significantly less informative than the Meleti model. So in other words, of the two, the Meleti model is more informative to forecast the earthquakes that were observed between 2010 and 2015 in Italy. So that is what this plot is telling us. So in another way, we can extrapolate, like, okay, to forecast earthquakes in California during those 5 years, a stronger hypothesis is to create zonations that have their own seismicity patterns, rather than adaptively smoothing the location of small earthquakes. So that's basically the way the PyCSEP tests work. We provide the modelers with insights about what are the hypotheses that are more consistent with the observations, and how we can improve our seismicity models in the future. We are not rejecting or accepting models. We're just providing information that could be useful for specific purposes. So that is what this Jupyter Notebook is doing.
Very nice.
Do you guys have any questions?
Yeah. Scott or Fabio, any questions in the Slack channel?
None at this time. If people work on this later and have follow-up questions, is the Slack channel the best way to continue to reach both of you?
Yes, I think that's good. So that's the current plan. So please post in the chat. So well, I want to kind of draw us to a conclusion here. I want to mention that there's another notebook in this tutorial session, and its focuses on something catalog-based forecasts. So I have kind of a more of a software-oriented kind of overview, but what we looked at were grid-based forecasts. Another kind of main category are catalog-based forecasts. And like the grid we just looked at, there's the grid-based forecasts for kind of well-defined region. This is kind of the grid for California that was set up for PyCSEP 1. But the new catalog-based forecasts are based on models, or applicable to models like ETAS, which produce synthetic catalogs. And basically PyCSEP 2 has been developing evaluation methods for these. The basic idea is that earthquake happens, and then there's kind of a range of possible or probable let's say aftershock sequences. So it's not a very active sequence, or it's a very productive sequence. And so the forecast, instead of producing a single kind of earthquake catalog, they produce a kind of a suite of catalogs that express these kind of possible outcomes or possible distribution of earthquakes. So USURF 3 is an example of that. And after, for example, Landers, they generated 10,000 stochastic event sets that might occur over the next year. And this basically drove the development of due forecast evaluations. So the typical categories of forecast evaluations are consistency tests, comparative tests, diagnostic tests. And then for each of a grid-based forecast, there's certain types of consistency tests, which might be are listed here. Catalog of type forecasts have their own set of consistency tests. So the implementation, what we find in this other notebook, is kind of an investigation into the catalog forecast and the evaluation methods there. So as a exercise, if you're interested in the catalog forecast, you can walk through this and go through this notebook, and it'll follow similar to what we just saw for the kind of a process of setting up, reading catalogs, but then evaluating the forecast. But in this case, it will use catalog-based forecast evaluation methods. Okay, so that's, just wanted to mention what that other notebook is there for you. But as far as our conclusions for this session, I want to thank you, Tono, for tuning in over the pond here for our session. But the main idea is that SCEC is a active international research collaboration, and it's got participant groups participating from multiple countries, and there not only there's kind of the research activity, but the software development, it's being managed as a community software development effort. So it's in some sense unique among the SCEC software developments that codes and code improvements are being contributed from an international group of developers, kind of extending the platform, for example, with methods or tools for their particular region that get integrated back into the larger code base. Here's some links to get an idea of the people involved and the organizations and the funding to show the real kind of large group of people involved. The documents for the PyCSEP can be found through here, the PyCSEP testing website. And we want to encourage you, welcome participation in CSEP activities. So if you're interested in either the science, you can contact Max Werner, who's a science lead for SCEC on the CSEP project, or if you're interested in the PyCSEP software and working on that, you can contact myself, who's the software lead at SCEC. So we encourage you, welcome you to join the CSEP community. Okay, so if there are any questions in the Slack, otherwise we'll monitor the Slack and
there is a question in the Slack. Felice, would you be willing to unmute and share it?
Okay, thank you. Thank you, Tono. It's a pleasure having you here teaching this to us. Thank you, everyone. I probably missed that part, but I was wondering if how much effort do you invest on, if you invest on including paleoseismicity or seismicity that is only written in ancient documents or by oral traditions, that probably there might be huge uncertainty in terms of the magnitude and the location, but are earthquakes that actually existed. And then probably they may have a return period, and we can expect they are going to happen again, but we don't have instrumental data for assessing them.
Thanks for your question, Felix. Also nice to talk to you. Well, if I understood well your question, yeah, actually some of the models that are currently being developed, evaluated in SCEC depend actually on fault data and historical seismicity. Of course, these are models that are defined in regions where this type of data has a higher availability and quality compared to other regions of the world. But yeah, such type of models exist, if that answers your question.
Yeah, probably for giving a precise example, what about the earthquake in Lisbon in 1755? So how can you include that kind of seismicity in your models? Because we know that there was a super large earthquake, devastating one, but we don't have any, as far as I know, we don't have any instrumental record of that earthquake, that's for sure. But what we as far as I remember, we have not ever had an earthquake like this in those years that we can compare. But the historical references told us that was a super huge and devastating earthquake.
Yes, actually, one of the things that we're currently working on at PyCSEP in general is to expand the way we represent our seismicity forecast, because currently what we're doing is representing them as point sources, not exactly as fault with fault geometries. That's something that we need to, that's something that we're currently working on as in order to support, say, probabilistic seismic hazard assessments. They depend typically on earthquake source models, and that's something that we're still not providing the community with. But yeah, that's something that is actually in the pipeline. So yeah, I hope we can do some good progress in the next couple of years in that regard. But yeah, that's definitely something we know, and we are going to incorporate hopefully soon. Thanks for your question.
Thank you.
Okay, well, we really appreciate the interest in our work here on PyCSEP. We hope that provides some good overview of the capabilities. PyCSEP is under active development, so please, if you're interested, check back and contact us if you're interested in collaborating with us. So at this point, I think we'll break for a little while, for maybe 30 minutes, and we'll come back online 10:45 to help people get set up for the next tutorial, which is the ground motion simulation validation. We will monitor the Slack channel over the interval, so please go ahead and post questions in there if you have. So thanks again for everyone for participating.